This video will be on your homework packet for the second FTC. For our first problem, we're going to have to find g at 3, but we're only given information in terms of g prime. So that means we're going to have to do some integrating in order to get back over to our original function. So starting out, we're going to set up the integral from 0 to 3 of g prime of x dx. And when we do that, we end up with g of x evaluated from 0 to 3, and then that can be g at 3 minus g at 0. The next part, we also know that the integral from 0 to 3 of g prime at x dx is also the bounded area. On our graph, if we look from 0 to 3, then we need to realize that we are also talking about the bounded area in this region, and then from up here, y'all are just going to have to pretend that's a straight line because this is about as good as it gets with me. Hey, that's pretty good. I'm kind of proud of that. So we also have this bounded area and then this small portion of the bounded area. So what we need to do is find the area here and the area here. Well, the area up here in this semicircle, well, really a quarter of the circle, well, we're going to have our regular area is pi r squared, but we really need pi times 2 squared, or radius squared, over 4. So really that area inside there, let me get rid of that big X, that area is just going to be pi. So let's go ahead and fix that. So this area is pi, and then we need to find the area over here with that triangle, and again we're just going to use our 1/2 base times height. And if we do that, notice we end up with that part of the circle as or that part of the triangle is going to be 3/2. So pi plus 3/2, that would be the other value for my integral from 0 to 3. So I have pi plus 3/2. Now what we're going to do is set this value equal to this value, and that hopefully will give us something that will allow us to solve for g at 3. Now we do need to remember that we have a given value for g at 0. G at 0 is 5. So if we set these equal, we have the equation g at 3 minus 5 equals pi plus 3/2. And then the last portion here is going to be to add our 5 over. So we have g at 3 equals pi plus 3/2 plus 5. In a similar manner, we will also solve for g at -2. So we are going to integrate again from 0, well, let's change our endpoints, from -2 to 0 of g prime of x dx, and that's going to give us g at x evaluated from -2 to 0, and then that's going to give us g at 0. Let me put in my equals, minus g at -2. And so we see that that's also going to be equal to 5 minus g at -2. And now we also go and we say, well, how much is the area there? So from -2 to 0 again of g prime at x dx. Let's see, how much is that bounded area? So we're going from -2 to 0. So from -2 to 0, well, from here to here, well, that's just going to be that other side, that other quarter of that semicircle. So that's also going to be pi. So they made the problem a little bit easier for us, thank goodness. So I know that from here to here we're going to have pi. And so now I can set up my equation and say that pi equals 5 minus g of negative 2. And so doing some rearranging, we see that g at negative 2 is equal to 5 minus pi. Okay, for this problem, or for the B part, we are looking for looking for the x-coordinate of each point of inflection of the graph of y equals g. So when we're looking for points of inflection, then that means we are looking for where, let's see, since we're talking about g, we're looking for g double prime of x equals 0 or is undefined. And we can, after we identify this, that's our possible point of inflection. And then to determine whether or not it's a true point of inflection, we have to have a sign change around g double prime. And we could say, since we're in the context of g prime, we could say g prime at x changes from increasing to decreasing. So that will help us figure out where we're going to have our points of inflection from increasing to decreasing. So let's look back up at our graph and let's see our possible points of inflection. It looks like we should have at x equals 0, that looks like 1. And let's see, at x equals 2. And finally at x equals 3. Now, it's possible some people want to select the value x equals negative 2 here. That one people want to choose, but keep in mind that my graph of g prime does not change from increasing to decreasing. We are still increasing here. So that's not a true point of inflection. Okay, in part C can be difficult to see in some places of it, but what the question is asking us to do is to find a critical point, or there might be more than one, for this function that is defined to be g of x minus 1/2 x squared. So in order for us to find critical points, that means we need a derivative set equal to 0. So what we're going to do here is we need to find that derivative. So h prime at x, let's see what that looks like. Well, h prime at x is going to be equal to g prime at x minus x. And to find a critical point, then we need to take this derivative, let it be equal to 0, or see where it might be undefined, and notice that we get g prime at x to be equal to x. So keep in mind on the graph that we have, the graph above is x comma g prime at x. And one of the first values that you see up there would be at x equals 3. Now so we need to do some kind of number analysis for x equals 3 to see if we can classify that critical point as a relative min or max. So let's look at what happens here. We're going to take x equals 3, and we need to look at some points around 3 to see what signs they have. So h prime at 2, that's going to be g prime at 2 minus 2. Well, g prime at 2, if we find that value, that is 0. So we see real quick 0 minus 2, we're going to have a negative value. So over on the other side of 3, let's check 4. Or we could even, we know the value of 5. So let's go ahead and check 5 and see. So h prime at 5 is going to be g prime at 5 minus 5. And g prime at 5 we see is negative 1. So we are still negative there. So it's kind of misleading because you want to say that 3 is a relative maximum, but we are looking for h prime. So x equals 3 is a neither for this case. We cannot classify that critical point as a relative min or max. Now, looking up at our graph, we do need to look at another place, and that's going to be up here with this equation from -2 all the way over here to +2. We see that there's a possibility there. So the equation for that is, since it is a semicircle, we are going to do the square root, and notice my radius is 2. So to solve for y here, now just in general, a quick review, the equation of the circle centered at 0, 0 would be x squared plus y squared, now this is for the whole circle, equals r squared, which is going to be 4. And so we need to solve for y because we want y equals, it is plus or minus 4 minus x squared, but we are just dealing with the top part. So it's just going to be the square root of 4 minus x squared. We're just looking at those positive values. So really, instead of y though, since we're talking about the graph of g prime, that's really just going to say g prime at x is equal to the square root of 4 minus x squared. So down here, we actually have another equation we can set up. So g prime we saw was the square root of 4 minus x squared, and that's going to be equal to x. And if we square both sides, we have 4 minus x squared equals x squared. And if we finish solving for x, x is going to be equal to, it is plus or minus the square root of 2, but again, we're just looking at the top half of that semicircle, so at x equals 2. So now what we have to do is look to see on each side what's going on there. Can we classify this one as a relative min or max? So again, let's go to h prime, and a value to the left of the square root of 2. Well, let's see, square root of 2, a value to the left. Well, I would imagine really just about any value here. And we really don't want to go all the way back. Let's see, let's choose maybe, if we look at our graph and we say, well, what about -1? So if we say h prime at -1, that's going to be g prime at -1 minus the -1, so plus 1. And if we look at our graph, we see that g prime at 1 is positive, and so a positive number plus 1, that's still going to be greater than 0. So let's look at a value on the other side of the square root of 2. So let's see, we could choose positive 2. That would be on the other side, I would think. So positive 2. Let's see, what are we going to get there? We're going to get g prime at 2, right? And then we're going to have minus 2. And so that's going to give us, let's see, a negative value, isn't it? That's going to be 0 minus 2. So that's going to be less than 0, so we can save ourselves some time. So notice we do have that sign change here. Our derivative goes from positive to negative, so h is going from increasing to decreasing. So x equals the square root of 2 is a relative max. This problem had quite a bit of work, but it was also worth 4 points, so it's worth the time to do it. Okay, for the first part of this, and this again is our review questions, we're writing our equation of a tangent line, which is something that I would think by now we do know how to do. Do keep in mind that if we're given this value here, that's the ordered pair 1, 2. And so we have everything we need for the equation of the tangent line except for the slope, and remember that's what our dy dx is going to find for us. So we need to evaluate this at the point 1, 2 So very quickly we see 1 times 2 cubed, and so we get 8. And so now we're ready to write that equation of that line. So we have y minus 2 equals 8 times x minus 1. And we can move that 2 over if you want to, or you can leave it like the above. Either one is perfectly okay. So there's our equation of the tangent line. And this was 2 points, and 2 points I want everyone to get. Okay, for part B, we're going to use the equation we wrote in part A, and we need to approximate the value of 1.1, and then we need to say, well, is that an overestimate or an underestimate of what the actual value of 1.1 is? So using our above line that we wrote, we're going to say f at 1.1 is going to be equal to, and then we had 2 plus 8 times 1.1 minus 1. And really we can stop there. You don't have to finish the problem. Now if you want to, of course, f of 1.1, and it's really not that difficult to go ahead and figure out, and we should end up with about 2.8. Now, to know whether or not this approximation is greater than or less than the actual value, we have to look at concavity, or the second derivative. Because, and let's think about this, if my graph is concave up, then my tangent line is going to be below the graph. So that means it's going to be less than. But if we're concave upwards, then it's going to be greater than. So very quickly we can plug our ordered pair into the second derivative to see what we get. And so if we see, let's see, our second derivative, and we're going to evaluate that at 1, 2, just kind of get us an idea for concavity at that particular point. So let's plug in, and we're going to have 8 times 1 plus 3 times 1 squared times, let's see, 2 squared. So all of that is going to be greater than 0, so we're concave up. So since our function is concave up at the point 1, 2, then we know that the actual approximation is going to be, the approximation is less than the actual value. So in our conclusion here, because it wants us to explain our reasoning, we are going to say that, let's see, what was our function's name? We're going to say f of x is concave up, and at the point 1, 2. So our approximation, so the approximation, let's see, so f at, our approximation, f at 1.1 would be below the curve. Let's see, so it would be below the curve, and thus the true, let's see, and thus the approximation is less than f at 1.1, the true value of 1.1. So again, with that, if it's over or under, you just go look at your concavity. Okay, so with our next problem, this is going to be where we separate and we integrate and we add c and we find c. And again, we have our initial condition here of 1, 2. So let's go through this. This is a great review for us. And so, and don't get these mixed up. You are using just your first derivative here. So the first step, always separate your variables. So I'm going to have dy over y cubed is going to be equal to, let's see, x dx. And then after we separate, then we go to integrate. So we're going to integrate, and it's okay to go ahead and rewrite that. Y to the negative 3 dy equals the integral of x dx. And remember, with integration, you are adding 1 to the exponent. So that's going to give me negative 2 divided by negative 2 equals, and again, that's going to be x squared over 2, and then plus c. Please remember that plus c. And now we're going to use our initial condition of, what was our 0.12, wasn't it? Yeah. So let's use our 0.12. I'm going to write it here so I don't forget it again. So 1, 2, that's going to give us negative 1 over 8 once we do the math there. And that's going to be equal to 1/2 plus c. And then we have negative 1/8 minus 1/2 equals c. And so our c value, once you get a common denominator, it looks like, let's see, 1, -1 minus 4, so negative 5 over 8 is our c value. So we separate, we integrate, we add c, we find c, and now let's go back and actually solve for y. So again, we had negative y to the negative 2 all over 2 plus equals x squared over 2, and now minus 5 over 8. We can multiply everything by 2. That's going to get us negative y to the negative 2. And you know what? Let's go ahead and multiply by the negative also. So that's going to give me negative x squared and plus 5 over 4. And wow, let's just raise both sides to the negative 1/2. That's going to just be terrible, isn't it? So, and we can leave this absolutely disgusting. Or if raising each side to the negative 1/2 you're not comfortable with, we can write it like this. This sometimes makes it a little easier to see. And then just swap places with your y squared in this other side. And so let me move this up. We're going to run out of space here. So we're going to have 1 over all this gobbledygook over here, plus 5 over 4 equals y squared. And then we do take the square root of both sides. And so we have the square root, and it's going to be positive. Remember to follow the sign of your y value in your initial condition. So we have 1 over negative x squared plus 5/4, and all of that's equal to y. All right, yay, that's a lot of algebra, but it's worth it because it is 5 points, and that's big points on the AP exam. Our next review problem we had was dealing with our Riemann sum. And so looking at part A, and hopefully part A is something you all can do. F prime at 4, and your estimating is approximately, and then remember it's between f at 5 minus f at 3, your good old slope formula, over 5 minus 3. And so that's going to give you negative 3, and that's worth 1 point. So please, please, please make sure you do that. All right, so for the next problem, part B, you need to divide up this integral. And let me swap colors so these don't run together here. So for part B, you can separate this and integrate from 2 to 13 of 3, and then minus 5 times the integral from 2 to 13 of f prime at x dx. And so if we integrate 3, so that's really 3x, isn't it? And really that's the same thing as saying, okay, 3, and then it's going to be times 13 minus 2, your top endpoint minus bottom endpoint, minus, and then this is going to end up being 5 times, and if you integrate the derivative, well, you're just left with those endpoints, f at 13 minus f at 2. And so we need to go up and look at our chart to get our values. And so let's see, it looks like we end up with all of this being equal to 8. All right, part C, good old left Riemann sum. So we will be using the leftmost part to determine the length of our rectangles. And so let's see, let's go through and set this up because we do need to show our work. So we need to find, well, the difference here, 3 minus 2. We have 3 minus 2 times the height here of 1 plus, and then 3 minus 5. So we have 2 times our leftmost, because it is a left Riemann sum, times 4. And then let's see, plus, and our next one would be 3 times negative 2, plus, and then we have 5 times, let's see, 3. And so that's going to be our Riemann sum. So let's see, that's going to give us 1 plus 8 minus 6 plus 15. And so let's see, that's 2. So it looks like we're going to get 18 here. Okay, so for part D, and part D is kind of a unique problem here. Let's see what we can do with this. So we suppose f prime at 5 is 3. And so just glancing through, we have to use the line tangent. Let's see, and it's tangent for, I'm reading the problem, use the line tangent to the graph at x equals 5 to show that f at 7 is less than or equal to 4. So let's go ahead and write the equation of the line tangent. So we have our slope, and at 5 we have negative 2. So we have everything we need, right? So y minus negative 2, so plus 2, equals 3 times x minus 5. So here we have y equals 3 times x minus 5 minus 2. So we have that line tangent. So now we need to see, well, we need to show that f at 7 is less than or equal to 4. Okay, so I would go ahead and substitute in our 7 here. And notice it also told us that f double prime is negative. So that's a big hint, nudge, nudge, that we are concave down. So that means that my graph is concave down, and so my tangent line is going to be sitting above. Okay, so that might be something we use here shortly. So let's see, well, what is the value of f at 7 with this tangent line? So it's going to be 3 times 2 minus 2, which is going to be 4. So we're seeing that, we see that f at 7, right here, using that, f at 7 is going to be, what was it, less than or equal to 4. So we've proven that point. Now we need to use the secant line. Oh no, the secant line of the graph of f on 5, 8 to show that f at 7 is greater than or equal to 4/3. Ooh, so let's see, can we find the secant line? Now we still have the same ordered pair here. We still have our ordered pair of, what was it, negative, or 2, 5. So that's going to be okay. But we need to find our slope here. So for our secant line, we need to find f at 8 minus f at 5 over 8 minus 5. And so our slope of our secant line is going to be 3 minus, because f at 8 is 3, minus a negative 2 all over 3, so we get 5/3. So now we can write the equation of our secant line. We found the slope of the secant line. So let's see, really the only difference is that we're going to change our slope. So we're still going to have y equals negative 2 plus, but our slope this time is going to change to 5/3 times, and let's see, x minus 5. So notice that we kept everything the same, but the slopes are going to change here. And so now we need to show that f at 7 is going to be greater than or equal to 4/3. So let's actually find the value of f at 7. This problem looked like it was going to be a whole lot more difficult than this. So we have negative 2 times 5/3 times, let's see, what were we plugging in? 7. So that's going to be times 2. And so let's see, what does that work out to be? So let's see here. So f at 7 for this one is going to be equal to, we have negative 2 plus 10/3. So f at 7 is going to be, it's going to be negative 6. So that's going to be 4/3. So we've shown that there also. So yay, we found our values and we've satisfied our problem. All right, so for the next problem, part A, from negative 5 to 5, we need to look and see for all values of x at which f has a relative maximum. All right, and then justify your answer. So let's go ahead and just start out with stating the rule, because that will justify our answer. So we know that f has a relative, and what were we finding? Max, when, and notice we're given the graph of f prime, so let's talk about f prime. So when f prime changes, okay, and let's see, maximum, so changes from a positive value to a negative value. All right, so there's our statement. So now let's go find, where does f prime change from a positive value to a negative value? So let's see, it looks like at x equals negative 3, that would be true, and at x equals 4. So here, we could write this happens at, or, so yeah, let's go ahead and do that. Let's just write it this way. So f, make sure you name your function, has a relative max at x equals negative 3 and x equals 4. All right, moving on to the next. So for part B, kind of the same, similar idea here, except for now we're talking about points of inflection. So, and we have to justify our answer. So a point of inflection in terms of f prime, a point of inflection is going to happen where f prime changes from increasing to decreasing or decreasing to increasing. So let's write that out. So f will have a point of inflection when f prime changes, and make sure you say increasing to decreasing, because increasing does not imply positive or negative. So f will have a point of inflection when f prime changes from increasing to decreasing, or, and then swap them, or decreasing to increasing. Right, so now that should make our picking out points of inflection a little bit easier. So we're going to say F has points of inflection at x equals. And looking at this, let's see, points of inflection increasing to decreasing, or decreasing, increasing right here. So -4. Let's see, and it looks like over here at -1. Yep, -1. So x equals -1, and it looks like at 2. All right, so again, and the previous question was worth 2 points, and this question itself is worth 2 points. Okay, next. All right, so find all the intervals on which the graph of f is concave up and also has a positive slope. Ooh, so there's 2 parts to this one. We have to be careful here. We want concave up and we want positive slope. So we have to look for, gosh, let's see, concave up. So that means f prime, let's see, concave up, f prime is increasing. So we have to look for that. F prime is increasing. And what else would we need to look for? And f prime is positive, right? And f prime is positive. So let's see if we can find those intervals. So let's go look at our graph. So f prime is increasing and positive. So it looks like that, of course, is going to happen from -5 to -4, positive and increasing. So -5 to -4. And where else would we have from positive and increasing? It looks like it's going to be from 1 to 2. That would be the other. So let's go ahead and say from -5 to 4, and from, what did we say, 1 to 2. Okay, next problem. All right, for the next problem, we have to find the absolute minimum. So we have to, whenever we have absolutes, that means that it's a good idea to set up a chart, and that'll help us see our different values and really give us a good way to organize them. If you're talking about an absolute minimum, you do need to check your endpoints, and notice this was over the closed interval from -5 to 5. And then we also need to check our relative min. So let's go find where our relative min would be. And our relative min should be over here at 1. So we also need to find that. Now do keep in mind we're looking at the graph of f prime, so we are going to have to do some kind of integrating with this, and we should have some points given to us. Earlier we were told that f at 1, let's see, let's go back up and look. F at 1 was equal to 3, so we're going to have to use that when we're setting up our integral. So f at 1 equals 3. So let's look at our first part. Let's see, f at 1, well, hey, we know that right there is 3, so that helps. So now we just need to check our endpoints. So let's go through and see, well, we can integrate here. Let's see, let's integrate. So from -5 to 1. Let's integrate that of f prime of x dx. My brain stopped working there for a minute. Sorry, folks. And so let's see, what is that going to give us? That's going to say f at 1. Let's go ahead and put it back up here. F at 1 minus, because we get f of x, and then we say top endpoint minus bottom endpoint minus f at negative 5. And so we see that f at 1 is 3, so 3 minus f at 5. And now we also need to go through and integrate like we did our previous problem and set up and say, well, okay, now we know also from negative 5 to 1 of f prime at x dx. Let's go find that area. So from negative 5 all the way over to positive 1. So let's check our areas and see what we have here. So from negative 5 to 3, and we have a semicircle here. So we have pi times our radius squared. So the radius is going to be 1, isn't it? And then we're going to divide it by 2. So this is going to be pi over 2. And then let's see, what else are we going to have here? Let's see, over on the other side, let's see, again, same idea here. So I'm going to find from here all the way to here, and our radius is going to be, well, from negative 3 to 1, so it looks like we're going to have a radius of 2, isn't it? So pi r squared, and divided by 2, so pi times our radius squared, so 4, divided by 2, so that's going to give us 2 pi, isn't it? But that 2 pi below the x-axis, so that's going to give us a negative 2 pi. So that looks like if we put those two areas together, that's going to give me a negative 3/2 pi. So let's go through and see. Let's come back down here. And so we have a negative 3/2 pi. And so now we have to set these things equal. So I have 3 minus f at 5 is equal to negative 3/2 pi. And so 3 plus 3/2 pi is equal to f at 5. So 3 plus 3/2 pi, let's see what we've got over here. So 3 plus 3/2 pi. Right, and so let's see, let's go through and see if we can't find the other side of this now. So it looks like 3 is still running for the minimum. Now again, we set up the same process here. So we're going to go through and integrate again. And let's see, our endpoints are going to be from 1 to 5 of f prime at x dx, and that's going to generate for us f at 5 minus f at 1. And so then we need to go up to our graph, and let's see, what's the value of our area here? So let's see, oh, I gotta get my pen back, sorry guys. So now we need to find, well, what is that true area from 1 to 5 of f prime at x dx? So 1 to 5, let's go look at our graph now. 1 all the way over to 5. So I need to erase some of this mess. Okay, so that's gone. Let's get back over to the pen, swap some coloring. Alright, so 1 to 5. So we're going to look at this triangle. So we have 1/2 the base. So the base is going to be 3. Comes a height, which is 2. So that area is 3. And then here, this area down here, we have, again, 1/2. Our base is 1. And our height is 1. So that's a half, but it is a negative half. So let's see. So let's go back down here. So we have 3 minus a half, which is going to be what? 2.5. So let's scroll back down here the way my monitor screen set up. So that was going to be, what did we say? 2.5. So we have f at 5 minus 1, f at 1, and we saw f at 1 is 3. That's going to be equal to 2.5, which very quickly we see if we add that 3 over, we're still going to have a larger value, 2.5 plus 3, which is certainly still greater than 3. So over here we found that our minimum value for f is 3. Now it's not always going to be what you're given, so please don't think that. But we can make the statement that and let's go ahead and make that statement, the absolute minimum value for, and what was our function for f, over the interval from -5 to 5 is 3. Alright. Alright, last problem in our pack. Yay! Woohoo! Celebration. Alright, so let's get her going. We need to find g at 0, which is going to be equal to the integral from -3 to 0 of f at t dt. Which means we've got to find our area from -3 to 0. So let's look and see, well, what shapes do we have over here that we can make from -3 to 0? So it kind of looks like with -3, of course, we have here. And then we have here, gosh, that almost looks like a trapezoid. So let's see, that's going to be 1/2. And then let's see, our height for this times the sum of the bases. So 1/2. Our height looks like it's going to be, looks like 3. Because it's going to be from here to here. So there's your height. Times the sum of your bases. And my base is going to be 2 plus 1. So that looks like we're going to have 9, isn't it? Yeah, 9/2. Alright, so that wasn't too bad. Again, do keep in mind your trapezoid's on its side, and there's base 1, and over here's base 2. Alright, so let's now find g prime of 0. Well, let's see. We do see that g prime at x is going to be equal to f of x. We need to establish that for our reader. And so, therefore, we're going to see that g prime at 0 is going to be equal to f at 0, and f at 0 is 1. So, great problem to get 2 more points. Alright, part B, we need to find all the values of x in the interval, open interval from -5 to 4, in which g attains a relative maximum. And we need to justify our answer. Of course we need to justify our answer. Why would we not? So let's see. Let's go ahead and state our justification. So we see that, let's see, g will have a relative maximum, max, when g prime of x changes from, so we're talking about relative max, so g is going from increasing to decreasing, so g prime changes from a positive value to a negative value. Alright, so let's see, we need to again state that we know g prime at x is going to be equal to f at x, and so therefore f of x changes from a positive to negative value at, from positive to negative at, and where do we change from positive to a negative? It looks like the only place that's going to happen for us is at x equals 3. going to happen right here. All right, and that was worth 2 more points. You got your justification and you got your point. All right, so for part C. For part C, we are looking for our absolute minimum. So again, hopefully by now, seeing that absolute minimum, we jumped straight to doing a chart. And we want an absolute minimum for G, so G of X. And so, of course, we need to check our endpoints, -5 and 4. But then, since we want an absolute min, we need to go see, well, where do we have a relative min? And again, remember, G prime is really going to be our function over here, f of x. And so, let's go over here and see, well, where else would I have a relative min? So, a relative min, that means we go from positive to, let's see, is it positive to negative or negative to positive? Negative to positive, isn't it? So that's going to happen at -4. So there's my other point that I need to go check, is at -4. All right, so let's go ahead and see. Well, are there some values that they told us in the problem itself? Well, no. Well, goodness. All right, so let's go ahead and start and see if we can't figure out, well, where is that going to happen? Goodness gracious. All right, so it'd been nice if they gave us some starting values. They were just being hateful in this problem. So let's start out with G at, let's see, -5. G at -5. Well, let's see, what is G at -5 going to look like? It's going to be the integral from, and let's see, from -3 to -5. Oh my. Well, we can't have that of f at t dt. So we're going to have to flop our sums for sure. So that's going to be the negative, and again from -5 to -3 of f at t dt. So let's go see what that value is. So let's come over here, and we're going from -5 to -3. So let's clean up our graph here a little bit. All right, -5 here to -3 is here. Oh, that looks great, because that looks like we're going to get a 0. How's 1/2 base times height? All right, so let's look at this bottom one. We have 1/2. Our base is 1, and times our height of 2. And then this one over here, well, that's again 1/2 our base times our height. Yay! So this one's negative, that one's going to be positive. So, oh, well, that worked out great. That one is 0. So let's fill that into our chart. We found that value to be 0. All right, now let's go and look at +4. And so again, same situation. We have to set up our integral. So G at 4 is going to be equal to the integral from -3 to 4 f at t dt. And so let's see, from -3 to 4. So let's look and see. I think we found, though, goodness, from -3 to 0, that was all the way back up in the very first problem. We already know the area of this trapezoid in here. We found that to be 9/2. So we already know that much. And so let's see, what else do we know on this one? Because this one looks like it might be a little bit of a booger here. So I'm going to go ahead and write down, well, we know 9/2 plus, and what else could we find here? And we're going all the way out to 4. So let's see, we got all the way to 4. We have here, well, we do have here, we could find that semicircle, couldn't we? And then subtract, or we could find the area of a rectangle here and then subtract out the semicircle. And that might be the best thing to do here. So why don't we find the area of our square? So, well, I say square, but let's see, what are our side lengths for that? We're going to have 1, and then 1, 2. So that's going to be 2, isn't it? Minus, and to get the square. And so, let's see, we have pi times our radius. So what's our radius going to be? It's going to be 1, but then we've got to divide that all over 2. So minus pi over 2, isn't it? That one was terrible. All right, well, we found it. So we've got 9/2 plus 2 minus pi over 2. I've already forgotten what the question's even asking me at this point. All right, and let's go through and see. It looks like the rest of these, let's see, 1/2 base times height. Yeah, they're going to cancel each other out. So that's all for that value. So, gosh, 9 plus 2. Let's see, that's going to be what? 4 13/2 minus pi over 2. So, let's see, for that value then, we have 13/2 minus pi over 2. But wait, there's more. Oh me. Alright, so g at negative 4. So let's go find g at negative 4. G at negative 4. Well, that's going to be the integral from negative 3 to negative 4 f at t dt. And now, of course, the endpoints need to be flipped. Holy endpoints Batman. So g at negative 4, we're going to flip our endpoints. So I have negative 4 to negative 3. Now all is right in the world because we've got our flipping endpoints flipped. And let's see, from, what do we got? From negative 4 to 3. Lordy day, I've got to do some erasing over here. So from negative 4, so where in the world is negative 4? Alright, negative 4, so negative 3, negative 4 to 3. So it's, oh, it was that little bitty, so right here to here. Oh, so it was 1, so I didn't have to erase that. Goofball me, that's a neck. So that's going to give me negative 1. Yay! So let's come over here and fill in our chart. So now we've got to figure out what in the crap the question was even asking to start with, which was an absolute minimum. And so I don't think 13/2 minus pi over 2 is going to be negative. So we have found the absolute minimum of, and what the heck was our function's name, of g is negative 1. And finally, the last problem. Rock and roll. Find all the values of x in the open interval from negative 5 to 4 to which g has a point of inflection. Alright, g has a point of inflection. So that means when I see point of inflection, I have to think second derivative. So g prime at x, we know that's equal to f at x. And then g double prime at x would then be equal to f prime at x. So that means we are looking for where does f prime at x equal 0, or f prime at x is undefined. And we also have to make sure we change from increasing to decreasing around those points. Alright, so let's scurry over to our graph. And let's see, where would be, now you can't use your endpoints, you're not differentiable at those endpoints, so don't even consider negative 5 and 4, just say nope, just say no to those. Alright, so very quickly I see x equals negative 3. We have a sharp turn there. We're not differentiable there. We change from increasing to decreasing. So x equals negative 3 should be 1. And let's see. Where else? I don't think we would have one at 1 because I don't change from increasing to decreasing. I'm still decreasing there. So at x equals 0, no, don't let that one fool ya. So let's see where else. Oh, right here though. There's a good one at x equals 1. And then up here at x equals 2. So there they all are. And we are finished. Woohoo!